Hello and welcome everyone to officially to our 24th FAIRWork webinar. And today the consortium, so many different people, will introduce you to the technical outcome of our FAIRWork project. So the design and all the ideas and concepts that we use to tackle the problem and the goal of FAIRWork, and of course the prototype, how we evaluated it or still evaluating it at the moment. And before I start with the details, I just want to give a short recap about the goal of FAIRWork. So what we try to do and how then you can see how we tackled it. So the goal is to support decision support, right decision support in complex systems, because they are getting more and more data that we have to reconsider. For example, from the production domain that we specialized on, sensor data from the machines or additional data sent to by all the partners. So we have a lot of data available, and additionally we have all the needs and data about the humans that we want to consider, so that the humans are recognized and it's better for the workers in there, and how we can tackle this with a platform or with a system that allows us to not only provide decision support to specific problems, but that we have a platform where we can handle different problems, ranging from assigning workers to production line to giving specific input on how to repair machines for the technicians, and how we can do this in one part. So what we need is shown here in this nice overview. We have algorithms that we need to process the data and provide this the results. So what you should do, so that we have different algorithms implemented for different scenarios and encoded in services. Then we have, of course, a knowledge base. So we need lots of data from the production side, digital twins from the humans created within the platform or from legacy systems, so that we can use them coherently. And in the heart lies the orchestrator, so that we have a management component that combines the different services with data, with the user interaction, and manages how we can then use this AI services to specific scenarios. But not only this implementation is part of FAIRWork, but also how we can configure it. So how can we identify the problems and translate them into really machine understandable configuration that can be then used to instantiate decision support for the specific scenarios. So this is also where this flexibility comes in, that we can configure and orchestrate these different scenarios. And without further ado, now we want to hand over to Rishiang, who will start the high-level architecture, so the basic structure of our system. And Rishiang, the stage is yours.
Thank you, Christian. And what you are seeing on your screen is the few high-level architecture components that we have identified in FAIRWork to support the decision support, to give the decision support to the end use case scenarios. So it will start from the left-hand side. That's what we have is a DAI-DSS configurator. The component itself has several sub-components like a configuration framework and the integration framework. The configuration framework has availability of tools like Adonis modeling framework, where we can create the decision process models based on the use case scenarios. And then the integration framework provides access to the tools like Olive microservice framework, and also ability to create flexible dashboards, like which can be used in the end as an user interface to invoke the services. And then we also have opportunity to create workflows using this orchestration and configuration environment. With the help of this decision process models and configuration information, we can then identify the required data sources, and that has been stored in the DAI-DSS knowledge base. This is the central data repository where all the required data to support the use case scenarios has been collected and stored and made available. And then the orchestrator here in the central is the key component, where it try to coordinate with all other components via REST services, and it's a central heart, we can say, in this system. And then it when the user starts interacting with the user interface, the inputs will be received through the orchestrator, and then orchestrator fetches the data from knowledge base. And then also it will decide based on the user request and the use case scenario. It will try to identify the right AI service. On the right hand side, we have a selection or a catalog of AI services that has been made available to support the use case scenarios, and based on the requirement, the right choice service will be picked by the orchestrator, and then the results will be computed and provided back to the user interface in an layout that is already pre-configured by the configurator. So these are the few building blocks, and then Marlena will try to give more insights into the use case scenarios.
You're
You are
muted.
muted.
Sorry. So yeah, thank you, Rishank. Basically, to have a short recap and overview on what challenges we were dealing with. I illustrated here multiple use cases and challenges we identified from our use case partners, CRF and Flex. And starting with the first one, which is workload balance. Here we aim to assist in fair worker allocation with the goal really to optimize this worker assignment to production lines while considering their medical conditions, preferences, and capabilities. Then the second use case is about production planning, which is more or less an extension of the fair worker allocation, and it deals really with optimizing orders, but also work allocation for a certain period of up to 2 weeks, with the goal to really facilitate and speed up the planning. Then the third use case is about the layoff material scenario, where we aim to support CRF in optimizing the container placement in trucks to reduce then the CO2 consumption for shipping. For Flex, we have identified 4 scenarios. The first one was machine maintenance. Here, we introduced a chatbot to really facilitate access to maintenance instructions for machines. And this information is distributed via multiple databases and hard to find. Then the document transformation scenario. Here, we aim to really reduce manual effort by transforming unstructured process instructions from Word to structured formats compliant with a specified target template. In the compliance use case, we aim to facilitate really the information access to often changing clean room regulations, which are critical to be fulfilled when entering the clean room. And lastly, we have the calibration document certification. Here the aim is to reduce manual and time-consuming effort by checking automatically for missing information or discrepancies or incorrect information in those documents and highlighting those issues. Altogether we have multiple prototypes ranging then from low maturity to higher one. You can see it under the AI enrichment column, and our prototypes are resulting in 3 demonstrators, which are then used and tested by our use case partners. And in this webinar, we are demonstrating then the final DAI-DSS prototype for one scenario, namely the production planning use case for optimizing this fair worker and order allocation. Next slide, please. Here we can see an example decision-making process for the use case fair worker allocation, and this is where we more or less started from. So together with the use case partners, we targeted a model-based approach to really specify requirements and derive really how decisions are made with models. Those models are also approved by the domain experts. Therefore, illustrated, you can see such a decision-making process of really how workers are allocated to a certain production line. And the goal here is to identify a fast and good solution for allocation while considering multiple decision parameters like, for example, the worker availability, the medical conditions of this worker, as not everyone is allowed to handle each geometry, and also worker capabilities and other aspects like the worker resilience must be considered for allocation. Next slide, please. As a more or less overview of the demonstrators part of our final DAI-DSS prototype. You can see here like different illustrations. As one main goal of FAIRWork is to allow really a flexibility by integrating various components and processes within one system. And for those, the individual configurations of the final DAI-DSS prototype show the different conceptual and technical realization approaches applied. So you can see here those flows, which we call AI patterns or AI interaction paths, placed over the the colored building blocks, let's say more or less. And those paths show now the orchestration of heterogeneous services and components, or AI assets, which we really envision between the building blocks of our high-level architecture, and which we aim to introduce to support really an efficient integration of the interplay and integration of various AI assets. Yeah, and those domain-specific AI interaction paths are realized using different implementation technologies. So we can, for example, use agentic approaches, we can use multi-agent system, workflows, no-code orchestrations, and so on. In the first workflow, more or less, you can see the concept for the scenario production planning demonstrator. So going through this very on a high level, where we get the configuration parameters and they are queried, then the knowledge base is queried, and the resulting data will be used by the AI to optimize the order and work allocation, and is shown in the UI. The second example shows then the realization of such a pattern for the agent-based worker allocation and ethical watchdog, which is very similar to the first path, but really illustrates then also the possibility of multiple negotiation rounds. Yeah, also in comparison, you can see on the right-hand side 2 other examples illustrated for our prototypes, and you can see clearly differing approaches from each other. In the following, we will see now, or we will detail now the technical realization of the scenario production planning, dealing with the worker and order allocation. And for this, I hand over to Rishank to show such an example.
Thank you, Marlene. Before going there, deep dive into how the use cases are supported by the AI services, I would like to give you an overview of how the components will interact with each other when they realized into a production environment. So here what you are seeing is the few high-level technical blocks that were as we discussed earlier. So the first starting block will be configurator, and if we click on that, you can see that the configurator configure required UI interface dashboards, which will be then displayed in the user interface. And then the configurator can also be used to create microservice workflows. And then these series of microservices as orchestrated as a workflow can be invoked by this multi-agent orchestrator. And then the configurator can also be used to store the decision process models, which were designed or co-created at the time of identifying the use cases and the required AI services. Once this information has been configured, this is the pre-configuration step. And then the users naturally can use the dashboards or the UI that has been made available via user interface, and then request for an support for a use case scenario. And then this request will be sent to the orchestrator, and the orchestrator will decide based on the user request and the availability of data. It will invoke the AI service, and this AI service will make some computations, and if it needs some data, then it will also be retrieved from the knowledge base, and based on the data, the AI service will do some analysis and gives us the required feedback as a decision support, and then the orchestrator will take these decision values and then make it available to the user interface. In addition to that, the orchestrator may also request additional data to enrich the decisions or the information provided by the enrichment services, and altogether will be shown in the user interface with the dashboards or graphics or metrics. This is the typical component to component interactions that are made during the decision support scenario. With that, I can hand it over to Harvig or
Yeah, to me. So basically, then starting with the building block, the pink building block on user interfaces. Here you can see more or less the user interface where we started from. So really the initial version. Yeah, it was for fair worker allocation prototype, and on the left side you can see this manual allocation component where decision makers really could select and assign manually for different lines. It also shows the individual worker properties like preferences, experience, and so on. In the middle, we include an automatic allocation possibility for different services. Here you can see it for multi-agent allocation service that the manager could then use as a suggestion. And on the right side, we have an overview of the orders, the line, and so on. Next slide, please. Exactly. And now you can see the adapted UI building block, or like the one we implemented then for production planning. And this, this visualizes the worker assignments across several orders for multiple production line and also for several days. So there are several functionalities available, starting from the left picture from the top. Yeah, on the production schedule, you can basically upload a production plan that includes really specific orders from the customers, quantity, geometry, and so on. The user can then also indicate the start date and the number of days to plan. And then there are other items that the user can specify, like, for example, he can choose the worker availability type, but also which AI service or optimization technique to use for each the order allocation and the work allocation. Yeah, another functionality is that for all parameters, an info button is available. So to help really the user understand the different possibilities he or she can select from. And one example of this info button is also shown for this availability type here. Yeah, on the button, you can then see the UI component that really illustrates in a timeline chart the allocation of the geometries to the different lines. Yeah, it also shows KPIs determining the overall, for example, worker experience and allocation for this specific allocation. Yeah, it is also possible that the user checks the details of such an order allocation for each line, which is illustrated by the picture on the right side. You can see for the geometry, the different aspects and, for example, workers allocated to produce this geometry for a certain time. And in case there are any issues, like, for example, too few workers are assigned, you can also see on the right picture on the bottom, a warning symbol is shown. Next slide, please. Yes, then coming to the second building block, which is the configurator, which is more or less a collection of tools really to speed up the configuration of the decision support system, and which is based on the microservice framework Olive. Olive in detail enables configuration of microservices and UI components. It enables to manage workflows, to create and deploy also web applications. In the picture on top, so the black boxes, you can see the Olive service definition catalog, where you basically can define UI components, you can define workflows, but also you can register and define AI services. On the Olive entry page, then, so the picture below, you can access different components for the DAI-DSS, like the modeling environment, knowledge base, workflow engine as orchestrator, and you can also configure a user interface of the service in 3 steps. So more or less, when pressing on one of the tiles, which is the create web application, you will be guided to the UI builder, where you can select a targeted service that you want to use and where you want to configure its user interface. And then by clicking on deploy, basically the solution is deployed as a web page in ABS, and you can use it. Next slide, please. Okay, then we come to the orchestrator building block, and here again I show you more or less where we started from in our initial prototype. So we can see here the orchestrator with workflow engine, and which is then advanced with the multi-agent orchestration in the final prototype for this use case. Yeah, the orchestrator more or less supports the definition and execution of different workflows using different engines, as we heard already, Netflix Conductor, or we could also use ABS step functions for more complex workflows, for example. Yeah, the workflow to be used can then be exposed through triggering APIs. And in the sample of worker allocation, we used Netflix Conductor to, on the one hand, retrieve data from the knowledge base, and also to trigger AI-based allocation services. With that, I would hand over to Rui, really showing now the multi-agent based orchestration of our final DAI-DSS production planning orchestrator.
Thank you, Marlene. The orchestrator was built in a modular approach and interconnects knowledge-based microservices and the user interface. It exposes a secure RESTful API to provide connectivity, and when a request is sent to this API to acquire the available microservices outputs, it triggers the creation of two distinct types of agents, a microservice agent and a data collector agent. Each microservice agent connects with a single microservice, considering that microservice requirements, and collects its output. These agents work autonomously, they run concurrently, ensuring that they operate independently, thus optimizing efficiency. The data collector agent is responsible for gathering and merging the data acquired by the currently active microservice agents to create and return the final output to the user interface. This approach makes the orchestrator secure and easily scalable to include more scenarios and its corresponding microservices, and allows an implementation of a decentralized orchestration of the available microservices. The microservice agents are dynamically created based on a configuration parameter. So for the scenario presented here, for the workload balance scenario, we have 3 different microservices, so we can have 1, 2, or 3 different microservices agents. Next slide, please. So for the production planning microservices, the overall operation is the one that I just described, considering both the microservice and data collector agents, but with an asynchronous implementation, given the time required to run the microservices algorithms. So tasks are created, and after the microservices have run, these tasks will contain the result, and the user interface can query the task for the result as soon as the task is created. So while the task is still not, or the results of the task are still not resulted, it will be given a pending return, but as soon as the algorithm has run, the result will be provided. Next slide, please. For these production planning microservices implemented by RWTH, the configuration includes more aspects such as setting the planning time interval, the worker's availability type, and choosing the algorithm or algorithms to use to solve the problem at hand. The majority of the services for this scenario follow a two-step approach. In the first step, the order to line allocation, there are 3 different alternatives. The second step, the worker to line allocation, we also have 3 methods with 4 different optimization variations. So the combination of both steps results in a total of 36 different services, and we still have 3 more. So for this range of services, a single one can be chosen, or all optimization variants for a selected for a method selected for a given combination for first step, second step can also be selected. And I hand over to Rishank.
Thank you, Ree. And in this slide, what we are looking at is the data aggregation part of our architecture. The primary component as we introduced, the DAI-DSS knowledge base will be the centralized step-based repository where all the required data will be stored. And here are few data generation units that you see underneath this block, that we have some event streams that can be originated from the application event factory or a factory data service. That's the icons you see on the left side of your screen. And then in our architecture, we have intelligent sensor box, which tries to bring the human factors or into the decision making process by collecting like the environment condition informations like temperature or air quality around the working environment. And similarly, the biosensors, which are like wearables, where it can be a smartwatch or a eyeglasses, where it will connect the psychological stress or strain, and all this information will be collected and then stored in the knowledge base. And then we have this external data asset marketplace, which can be used to store additional data that is required to train or do more enrichment for AI service models. And the knowledge base will provide access to this data. In the next slide, what you see is the realization of an CRF workload balance use case scenario. And here you see what you see these in the picture is in a node instance diagram. So we have several placeholders to store the production line information, and then operator preferences, and similarly the operator availability. All this information has been represented as an breakdown structure in the system, and then this is made available via REST APIs, and subsequently the orchestrator may request the required data to take the information from the knowledge base and then provide it to the AI service to compute the result and give it back to the user for the decision making process. So that's the knowledge base, and I can now give it back to Herwig, who can explain more about our this.
Already said, we are collecting within the intelligent sensor box with two types of sensors, variables which measure, for example, human heart rate or respiratory frequency. And with these sensors, for example, we measure the stress of the people, which can, of course, be variable depending on the workload, depending on the current situation, on the weather, etc. And from these sensors, we get and calculate the resilience score, which consider also this aspect. And this is relevant to see if the people have the right focus, the right attention, because it's important that you are in a special flow in this type of situation. You make less mistakes, which is highly relevant in the industry. And this we're doing with these measures, with the sensors. And what Rishi also mentioned, we are using also CO2 sensors, for example, to measure the CO2 in offices or also in the shop floor, and this can be considered as well. The important stuff is this resilience score, and we store this in our own database, and then we send it further to the knowledge base to some extent to include that, for example, in the workload balance services, etc. Next slide, please. And another aspect what we used, we can also include in this knowledge base what we can say to have an API to external data services, and this is also one aspect. This can be done by APIs or message queues for storing the data sets. We're using a data hub, and this is also part of the building blocks. Okay, and now hand over to the next presenter.
Yes, so let me briefly recap what we consider as AI in the scope of FAIRWork. So we talk a lot about AI, and whenever we say so, we mean one of the three categories basically. So we have the agent-based approaches, which we saw earlier presented by Moore. Then we have ML approaches, which include technologies like neural networks, decision tree learning, so boosting trees, random forests, and these kind of algorithms, and reinforcement learning. We also consider symbolic AI, which can be fuzzy logic or a fixed set of rules, but also a bit more sophisticated techniques like constraint programming, for example. And now I would like to talk about two services in more detail, which is now on the next slide, the fair worker allocation. So on a given day, we have people present at work, and we have the production lines. Here it is on the right-hand side. You can see UTE-1, UTE-4, and UTE-8, which require some personnel to operate. So UTE-1 requires 4 personnel to be operated, UTE-4, 6, and UTE-8, 2 personnel. And then we have some workers that are present. And the way we can tackle this issue here, this assignment problem that we have, is by, what you see here on the left-hand side in the diagram. We basically enumerate all workers. So we have a list of workers. And then on the right side here under task, we have a list of the slots that need to be filled with workers. Then we draw connection lines between the slots and the workers. So what you see here, for example, worker number 3 can work on UTE-4 on slot 2 or 3, but worker 2, for example, cannot work on UTE-4 due to training or medical constraints. So the lines represent all the possibilities to allocate a worker. And for each of these lines, we calculate a cost. And the cost is based on the experience of the worker, on the resilience, and on the preference. So if the worker has a high preference for a task, for working on the machine, the cost will be lower. If the worker has a high resilience, the cost will be lower. And so I mentioned resilience and preference. Yeah, so these basically add up to the total cost, and what the FAIRWork allocation service is doing. The FAIRWork allocation service chooses from the set of possibilities here, the possibilities such that the total cost is minimal, and then therefore finds the most optimal work allocation in that given scenario. Then we go to the next service, or to the next use case, which is the planning. So in the planning, we consider a time frame of like 2 weeks about. So before, it was only like a single day, a single shift. Now we are looking at a whole week or two. And in there, we try to allocate basically the tasks that need to be performed on the machines, and then come up with a plan which workers will be working on these machines. So, and for that, we chose a 2-layered approach. In the first layer, we do the assignment of tasks to the machines, and afterwards we have a look at the workers and allocate the workers to the slots like we saw beforehand. So if you go to the next slide now, the layer 1 problem is essentially we have a set of goods that we need to produce. So these are the geometries here indicated on the right hand side, and each geometry may be produced on different lines. So the upper geometry can be produced on UTE-4 or UTE-1. So these are the alternatives. On UTE-1, it takes a bit longer than on UTE-4. And for geometry, the one in the middle, that could be produced on all of the lines. And the last one can only be processed on UTE-8, for example. And the problem we are facing now here is we need to find, for each geometry, one of the lines it should be processed on. And we need to align the boxes essentially in time so that they do not overlap, which means that there's only one thing running on the machine at a given time. So the problem is picking a colored box and then arranging the box such that the rectangles do not overlap with the same color. So that's done here. So that was basically what layer 1 is doing. And afterwards, we take the shift plan and have a look at the workers that are present in a given time frame. So here, whenever there is a vertical dotted dashed line, that represents basically a shift. And what we need to do now here is to assign the workers that are present according to a shift plan to the specific machine. So when you play the animation now, that's basically what the second layer of this approach is doing. So, and for the first layer, we had a constraint programming approach that works pretty well. And for the second layer, we have also we have 3 options here, which Rui also indicated beforehand, which is first, the CP approach is basically what we saw beforehand. Do the same thing as we did before, and for each of these slots, for each of these intervals between like the dashed lines. Then we have also the possibility to do the same task with reinforcement learning. So in reinforcement learning, an agent does these allocations over and over again and tries to gather experience and find patterns to do this allocation in a way that is optimal for, or which fits the user needs. And then we also have the possibility to do it in a Monte Carlo tree search approach, which is basically just picking one at a time and then trying out, simulating what would be if I put the one worker in this slot, and just iteratively builds up the solution. So these are the approaches that we implemented in FAIRWork. And now we have a small video of how to call the service actually, where you just then in the end pick your schedule file or the order file and trigger the service. Then it takes a bit of compute, I think around 8 to 10 seconds. and then you will get the result in the UI. So it does perform like both of the layers sequentially and comes in up with the results in the UI. Here we go. And then, yeah, you basically see now an interactive version of what Marlene showed earlier on in the screenshot. Okay, that's it from my side. And back to, who is it?
It's me. Hello,
Oh.
Alex. Gustavo.
To Gustavo. Here you go.
Thank you, Alex. So I'll present the ethical watchdog developed in the project. The objective of this decision-making process is to assist the decision maker in allocating workers to production lines, and at the end, to be able to evaluate the system's all recommendation regarding ethical issues that are relevant to the use case and that the proposed solution might face, and then propose a recommendation that is not only driven by performance, but also ethically aligned with societal values. It starts with the decision maker triggering the decision process by asking for an allocation of available workers to the production lines. The system starts a negotiation process, taking on workers' resilience and preference parameters regarding the production lines. And based on that, the workers are ranked from the most to the least suitables to the given production lines. With that, the decision maker has a recommendation to allocate workers based on their performance level translated as their resilience level and preference of being allocated to that specific line. However, this first negotiation doesn't consider the ethical sphere of this decision process. After this first negotiation round, the decision maker can opt to evaluate the outcome through an ethical watchdog. The watchdog monitors what is the outcome and whether it respects any threshold defining the ethical criteria. If it does, the ethical watchdog raises an alarm to the decision maker to alert the fact. With that, the decision maker takes the watchdog output and can then choose to trigger another negotiation round, considering all the most relevant workers from the previous round. This new round takes these workers and rearranges their position in the rank, enforcing the ethical criteria established for the use case. If there are available workers that fulfill the ethical requirements, we expect to have a recommendation of worker allocation that address the ethical issues. In summary, the watchdog assists the decision maker to achieve an ethically aligned decision without neglecting performance aspects of the decision process. I'd like to share now my screen to show the service running. And then, yes, and I will choose this screen. Can you see it? So here we have an example of an allocation. So I want to have workers allocated to line 17. I want to receive a recommendation for that based on what I just explained. And then I can see here already that the age criteria for this specific use case is not being satisfied. So as a decision maker, I can choose to trigger a negotiation process that will enforce these ethical criteria. And then here I have another solution that uses these most suitable workers and enforce these ethical criteria to propose a new set of workers to be allocated. And I can do this for these 3 available production lines and access all of this data regarding the workers I'm interested in. So with that, I show you briefly a possible solution for this ethically aligned watchdog agent enforcing all of these ideas of societal values aligned in a decision-making process, not only looking into performance. So thank you. I hand over to Marlene.
So thank you, Gustavo. Yeah, more or less as a short summary, what we saw today we presented more or less one demonstrator on the scenario production planning and FAIRWork allocation, and which is more or less one configuration of the final DAI-DSS prototype. And we also showed for this more or less the evolution from the initial version to like what we have in the final prototype. So we have seen in the pink box the UI components for allocating the orders and workers to the line. In the blue box and the configurator box, we saw how Olive was used to configure services and the UI, but also how knowledge and models were used as an input for this configuration. In the building block orchestrator, so in the gray box, we saw two examples of configured workflows using, on the one hand, for the initial prototype, the Netflix conductor, and then its evolution with the multi-agent based orchestrator. In the orange box, there was a short introduction on the knowledge base and the data we received from the use cases, but also the integration with the human factors and the resilience scores and so on. In the green box on the right side, we saw two introduced examples of AI services. So on the one hand, we saw the hybrid approach using this constraint programming, the reinforced learning approach, or the Monte Carlo tree search. And second, Gustavo also illustrated this agent-based approach and the ethical watchdog method. One click, Christian. So, yeah, however, as we have like a full prototype, a full final prototype with different scenarios and also including different configuration of different decision scenarios, characterized by really multiple AI services concepts, but also domain-specific orchestration within the DAI-DSS building blocks. And this domain-specific orchestration was depicted more or less in this instantiated interaction path that I introduced in the beginning. So there are some more components in the final prototype than just what we have presented today. Next slide. Yeah, and as a short outlook, where we're going to with our FAIRWork DAI-DSS architecture and prototype, we really aim to contribute to a foundation to an European reference framework, so depicting domain knowledge, roles, processes, organizational and domain aspects, but also for an architecture focusing on technical aspects, really promoting a trusted and sustainable AI ecosystems. The idea is to build upon standards, protocols or patterns between different AI assets, like, for example, model context protocols, BPMN modeling standards, or also data standards or data sharing standards. And the idea is to instantiate our concept with also European technologies coming from research, like, for example, UC7B, or coming from industry like Mistral, and try it out and apply it to those, and also to operate and test our concepts in European infrastructures, like, for example, in AI factories. Yeah, for high performance and also high availability of AI system operation, we envision really then domain-specific AI interaction patterns, where I've shown like some very concrete example for the FAIRWork prototypes. With this, I would say thank you very much, and I would hand over to Christian. Yeah.
So thank you very much for all the presenters and their interesting inputs and thoughts, and what report on what they've done in FAIRWork. And now we have time for questions. If there are any, questions by the participants? Now that we have all the experts here, then thank you very much. If there's no questions or anything else still there, then our next webinar will be in the mid of June, focusing on optimization services by our colleague GR. And with this, have a nice weekend and see you hopefully next time. Bye.
Thank you. Bye.
Bye bye.
Bye.
Thank you
Have a
very
nice
much.
weekend.
Bye.
Thank you. Bye.